Okay, can you hear me? All right. So what I'm going to talk about today is joint work with Alex Breuer and Yifeng Cui at the San Diego Supercomputer Center, and also with Chuck Yont and Alex Heinecke at Intel. So our application is called AWP-ODC. It's an earthquake simulation code. So just a quick overview of what I'm going to talk about. So firstly, I'll introduce what the application is, why it matters, and a little bit about the numerics behind it. Then I'll talk about our experiences and the lessons we've learned tuning the application for Xeon Phi 2nd generation. One of the key techniques we use is something called vector folding. So I'll spend a while talking about what that is and evaluating the performance it gives us. And then finally, I'll present some performance results. So we compare the performance mostly to GPUs, but also to Xeons, and a little bit of a comparison across different models of the Xeon Phi. So that's a quick overview. So what is the application? So like I said, it's called AWP-ODC, which stands for Anelastic Wave Propagation, and then ODC are the initials of the three primary developers. So it's an earthquake simulating code. So it simulates the propagation of a seismic wave through a three-dimensional viscoelastic medium after a fault ruptures. So it's used pretty extensively by the Southern California Earthquake Center, which is called SCEC usually. It started out about 20 years ago as a Fortran code, but it's existed in a lot of different forms over the last 20 years. So there's been a Fortran version, it's been in C with CUDA, the new version is C++, and it's a hybrid MPI OpenMP code. So recently, the last 5 years, say, it's primarily ran on GPU-accelerated supercomputers. For example, the Titan cluster. So most of our comparisons will be with GPUs rather than with Xeons. And then finally, just as a side note, the first ever open source release was a couple of months ago, and that's why we've appended the OS on the end. So now it's AWP-ODC-OS, but I'm just going to call it AWP. So. Okay, so just to motivate the application a little bit, so this is a FEMA report from 2000. Obviously, earthquakes are a problem. That's not shocking. This kind of emphasizes the importance, particularly in Southern California. But it's not. It's kind of a nationwide problem, as you can see. Actually, you can kind of make out a little bit of a blip around Chicago. And so although AWP is primarily used in Southern California, it's been applied elsewhere too. So the code has simulated a fault rupture in the Cascadia Fault in the Northwest. So it's developed in Southern California, but kind of used nationally. Okay. This kind of emphasizes our needs. So here's a chart of a couple of our biggest simulations. That's in kind of the red-purple color. And an extrapolated line of what our expected future supercomputing needs are. And then also we've got the NSF DOE machines and the top 500 #1 machine. And you can see that the SCEC needs are kind of growing faster than machines are being built. So at the current rate, we'll need more capacity than any machine can provide. Or why we need all this capacity. So here's one example of why we need high-performance computing. So when you're doing a simulation like this, if you want to do a damage forecast, human structures, buildings, are particularly susceptible to high-frequency seismic waves. And if you want to double the frequency accuracy, so if you want to see twice as high frequencies, to go from 1 Hertz to 2 Hertz, for example, you need a factor of 16 increase in the number of points, because you need to halve each spatial dimension and also the time dimension. So for a small increase in frequency, you need a big increase in the computational load. So that's one of the reasons why the computational demands are so high. So it's important for us to run on as many different machines as we can, on GPUs, on Xeon Phi, and to get every little bit of performance we can out of it. That's crucial. I should say also, so this is a very widely used code, and it's an important code. I mean, this M8 simulation in 2010, at the time, was the biggest earthquake simulation ever completed. For some definition of biggest, it's a little bit vague, but okay. So I'll talk a little bit more about the background in a second, but I just want to give a preview of the kind of the final results, because that's what people here are interested in. So like I said, we primarily compare with GPUs. Most stories we've heard today and yesterday have kind of been of the following form. So you start off with a Xeon code that wasn't optimized. You run that on KNL and it doesn't do so well. And then you tune it for KNL and then it does really well. And then you bring those optimizations back to Xeon. So our story isn't like that because we started with GPUs, really. So we started off with the GPU code. We brought it onto KNL, did some tuning, and then we tried running that on Xeons with the same kind of tweaks. So this number on the left here, it's a Xeon. It's a single socket, by the way, unlike a lot of the numbers presented this week have been dual socket numbers. So this is a single socket multiplied by 2 if you want to pretend it's a dual socket. So this isn't quite an unoptimized code. It's not quite an optimized code either because we haven't really been focusing on Xeons. But it acts as sort of a baseline. So we've got the Xeon as a baseline, and the real important comparison for us is more the GPU cards here. So the main takeaway is on a 7250, we're getting faster than even the Titan X Pascal, which is really the cutting edge GPU. So that's the big takeaway for us. I'm going to talk a bit more about these performance results later. I want to go back to the numerics, and then I'll talk about the different techniques we use to tune the application. OK, so here are the numerics. It's a finite difference code, uses a staggered grid scheme. It's fourth order accurate in space and second order accurate in time. There are quite a few grids going on here. So we've got 15 grids that are written to at each time step, plus an 11 additional read-only grids. And we've got a couple of different stencils. So for 9 of the grids, we use this top left stencil. So to update the stress and velocity grids, we use this stencil here. It's a 13-point stencil, so it's symmetric in each direction of radius 2. For the memory update variables, I'm not going to talk about what they mean. They control frequency-dependent attenuation, a physical feature that's not super important for the purpose of this talk. But it's the top right stencil here. It's the green one. It's a 9-point stencil. And then finally, we've got boundary conditions on the z = 0 boundary, a free surface boundary. And that's this stencil here. So I'll come back and talk about these stencils every now and then. The most important stencil is the top left guy, though, this stencil right here. So the shape of this stencil will be important when we talk about vector folding. OK, and then finally, just a quick, to wrap up the numeric overview, here's a summary of the control flow of the application. So a couple of these steps will be important later on. So firstly, when we run the application, we've got this initialization step. So that sets up all of the input mesh that controls the geological, the numbers that control, I guess, the geological region itself, the material parameters. So that happens at the start, and there's quite a bit of pre-processing there. So it's slightly computationally expensive. But then the most important part is this main loop then. So we update the velocity, then we do a boundary update, we update the stress, then we do another boundary update, and then we update the source term and output. For tuning, the 2 most important things are these green boxes, which are 2 stencil updates with the stencils we saw in the previous slides. And these 2 green boxes take up the vast majority of our time. So these are the guys we really need to tune. The update boundary steps also use stencils. We tune those a little bit too, but I'm not going to talk about that so much. So the key thing really are these 2 green boxes. OK, so I mentioned we've got this technique vector folding that we use to speed up our stencil computations. So really, it's a data layout scheme designed to improve spatial locality. So it's used for stencil codes. Here's a simple sort of 2D example of what's going on. The idea is simple, though. So you take a traditionally laid out grid, and rather than storing it in the traditional way, you try to store it as an array of small SIMD-sized blocks. So let's look at the picture on the top right. So forget about all the colors for a second. So it's just a 2D array. I think it's 10 by 9. And assume that memory is increasing from left to right and from top to bottom. So that's the traditional layout on the top. But then you could store it a different way. So break it up into 2 by 4 blocks, and then store those blocks consecutively. So first you store this orange thing on the top left. It's the first thing you store. Next, you store the green guys. So it's a little bit kind of out of order now. But we'll see that this will actually improve the data locality when we apply our stencils. So to generate the vector folding data structures and the kernels that use them, we use the tool called YASK, which I'll talk a little bit more about later. So that's developed by Xeon of Intel. So he's here. If you've got any questions about YASK, you can ask him. And OK, so that's a sort of a two-dimensional picture. I think it's good then to look at a three-dimensional picture to see why this would actually help with the stencil code. So here's a stencil of radius 2. So the orange, is it orange for you? Yeah, so the orange block here represents one cache line. So if you want to update one cache line with a traditional memory layout, on average, how many cache lines do you need to access for a stencil with radius 2? So it'll be 9. So in the, let's say Z is the leading direction. Let's ignore the leading direction for a second. In the Y direction, probably none of the adjacent blocks will be in cache still. So you need to look at 2 guys up and 2 guys down in the Y direction. That's 4 cache lines. Similarly, in the X direction, 2 to the left and 2 to the right. But in the Z direction, the previous cache line will still be in cache, even L1 cache. So on average, you only need to access 1 new guy as you iterate through the domain in the Z direction. So in total, this is 9 cache lines you got to touch. And now let's look at a vector folded layout and see how many cache lines you should need to touch. So okay, the picture's changed now. So instead of looking at the traditional memory layout, let's look at a 4 by 4 by 1 vector folding. So that's 4 by 4 in the X and Y direction and no folding in the Z direction. So now it looks something like this. So you've got the blue guy in the middle is the guy you're trying to update. So how many cache lines do you need to look at? So again, in the Z direction, you should only look at 1 new guy because, well, the previous 2 are still going to be in cache. The next guy is still in cache. It's just the guy 2 ahead that'll be new. But this time in the Y direction, you just need to look at 1 guy each way because the stencil's radius 2, but each of these blocks is radius 4. So basically, we've reduced the number of cache lines you need to look at from 9 to 5, which is clearly an improvement. So that's the idea behind vector folding. And the effect is even more pronounced with stencils of greater radius. You can see that. So OK, so what is this YASK thing? So it stands for yet another stencil kernel, like I said, developed at Intel by Xeon. It's not a library. So it's more of a kernel, a stencil proxy. It's an evaluating tool. So you specify your kernel, you run it through a code generator, and then you can specify different options like different vector fold sizes or cache blocking, loop unrolling, and so on. And it'll tell you what the performance is in a proxy type environment. So it's like a mini app, as other people have talked about today. It's open source. It's available at this website. So Intel's GitHub/YASK. And like I said, it's not a library, but it does output vectorized code, which then you can integrate, if you like, into your applications. That's what we do. So we take the generated code and integrate it into AWP. So here's an idea of the performance. So this isn't full application performance. This is proxy performance. So running through the YASK proxy, how well does the vector folding do? So the guy on the left is traditional vectorization. Because if you've got a vector fold that's just in the leading direction, that's like doing nothing at all. So that's kind of a baseline. The performance is measured here in lattice update points per second. That's how many points you can update all 15 grids on. How many of those, sorry, so 1 lattice update point is updating all 15 grids. So this is measuring how many of those updates can you do per second in millions. So with no vector folding, you get about 812 M loops. And then you can see for various sizes of vector folding, you get different performances. The best performance is here by 4 by 4 by 1. And it's a performance increase of about 1.6. So it really does help. OK, so that is vector folding. So like I said, this isn't full application performance. This is performance from the proxy. And I should also say, so this is running on a bin 3. It's a 7210. It's one of these DAP nodes that Joe Curley advertised yesterday. So later performance numbers will be on the 7250, but this one is on the 7210. So, oh, and also, yes, this is all running out of MCDRAM in flat mode. I'll talk about cache mode a little bit later, but these numbers are from MCDRAM flat. All right, so on to the performance results. So these are the same numbers as before, but it's a little bit more explicit this time. So the last two numbers are preliminary. I really want to emphasize that. So the 7250 number we only got last week. That's why it's preliminary. The Titan X number, we only had very brief access to the Pascal card. But the 7250 really the 7250 really does outperform Titan X and consistently. And the 7250 number will go up. So it's preliminary partly because we only got the number last week, but also partly because we're still in the middle of tuning it. So I have no doubt that this number on the right will increase. So we also compare here with the 7210. The 7210 does surprisingly well compared to the 7250. And this is really an artifact of the fact that our 7210 node is super well tuned and the 7250 node isn't quite so well tuned. I'll talk a little bit more about that later probably. So, okay, we compare with Titan X. We also compare with some legacy graphics cards. So we've got the K20X here, that's a Kepler card. We've got the K80. So a K80 is really just two K20s put together. So we measure single card performance here for fairness. Kind of like we measure the single socket of the Xeon. And then we've also got a Maxwell number, that's the M40. And the 7250 does better than all of these, more than twice as good as the K20X. Okay, so the comparison, so how did we do this comparison? Obviously the codes have to be different because on Xeon Phi you're running a C, C++ code, and to run on the graphics cards you need to use CUDA. So the codes are different, but the graphics card numbers are the product of, so how to say this? So the way we set up this performance comparison was we had our people that work on GPUs produce their best number after tuning. And we, the people working on the Xeon Phi, produced our best number after tuning. So although the codes are different, this is the best both teams could do. And it's both simulations were computing the same physics with very similar code. So it is a fair comparison, even if it's not exactly the same code. So, okay, these are our overall performance numbers. So let's talk about the various different tuning parameters we did and a quick comparison of memory modes. So this is kind of just a quick sanity check. So we measured our performance as we scaled the number of cores. So it's really just, like I said, a sanity check for our OpenMP. So you would expect that it should scale roughly linearly. I mean, we're bandwidth bound because we're a stencil code with pretty low arithmetic intensity, so you'd expect we should be bandwidth bound. And then, so you should expect that the performance should scale roughly linearly with the number of cores up until you hit about 48 or 50 cores. Then there's kind of a diminishing returns because you saturate memory bandwidth before you get to 64 cores. So this is on a 7210 again, so we don't go beyond 64 cores because there are only 64 cores. Actually, the top number here is 63 cores because we leave one core for the OS itself. So you can see here the performance does follow the stream numbers here a bit. So on the top right, you've got the stream triad benchmark. So that does increase linearly up to 48 cores, and then you get a bit of a drop-off when you get to 63. And our performance does the same thing. The drop-off isn't quite as pronounced, but it is there. Hopefully you can see it. So how accurate is the stream triad benchmark for our purposes? Well, it looks to be pretty accurate, but it's sort of an open question. I mean, stream triad is a read-write ratio of 2. Our application has a read-write ratio of 5 to 1. So that does change things a little bit. Okay, so that's scaling with cores. Like I said, this really does suggest that the memory bandwidth is the thing that's limiting performance here. So let's dive a little deeper into that, and let's use VTune to see what our bandwidth actually is. So this is the same setup as the previous slide. So we scale the number of cores and measure the performance. And this time, so we've got stream, but we also then look at our VTune output, look at the times in the middle of a kernel execution, and measure the sustained bandwidth in the middle of a kernel execution. So these AWP numbers are not application-wide bandwidth. That average is kind of ruined by things like initialization and a few other things. But during kernel execution, this is the bandwidth we get. And you can see it really does follow the stream triad benchmark. It tapers off a little bit at the end. That's noticeable. Whether that's an artifact of the different read-write ratio or something else, it's not clear. Okay, so I think the summary here is that really we're bound by the memory bandwidth of the machine. So KNL is quite good for us because its MCDRAM bandwidth is so high. Actually, if you take all those performance numbers from 2 slides ago and just look at each machine, look at the bandwidth it achieves, and work out what performance you'd expect based on the bandwidth, it's a really, really accurate predictor of what performance you should get. So bandwidth really is the most important thing for us. Okay. So with that said, because bandwidth is the thing we care about, it makes sense to try the different memory modes of the machine to see how they affect things. We much prefer flat mode to cache mode, because flat mode gives us that control. But some of the machines like TAC will presumably run mostly in cache mode, so it's important for us to see how well cache mode performs. And I mean, the good news is cache mode does pretty well. We've kind of got a couple of benchmark numbers here. On the left, we've got that Xeon benchmark number running out of the Xeon's DDR. On the very right, we've got the flat mode MCDRAM performance. And then on the second from the left, we've got the KNL node running straight out of DDR. So these are 3 sort of benchmark numbers to compare the cache mode performance to. And you can see that if we're running in cache mode with a problem size that fits more or less inside MCDRAM, that our performance is very close to the flat mode results. There's a little bit of a drop, about a 6% drop, but that's not so bad. We don't like it, but it's not terrible. Then understandably, as the problem gets bigger and bigger, you go outside of MCDRAM cache, and then the performance drops. But even up as far as 60 gigabytes, you're still quite a bit better than DDR, so that's a good sign. Okay, in summary is cache mode is a viable option, and that's good for us. So these runs were all done on the Stampede extension. I've written Stampede 1.5 in the slide, but I was told by the tech guys yesterday I shouldn't call it that. So I think these numbers should go up a little bit as well. I mean, on Stampede at the moment, the stream triad gives about 475 gigabytes per second. Our own 7210 node is giving 460 gigabytes per second, which is pretty close. And there should be a much bigger gap between the 7210 and the 7250. So I expect tax numbers will increase over the next couple of weeks as they leave early access. Okay, so just a really quick couple of lessons we've learned, and just small things, but surprisingly the small things combined add up to almost as much as some of the harder things we've done too, so it's worth mentioning these things really quickly. So this is a kernel bootline option known to anyone, I'm sure, that runs a HPC system, but maybe not to the computational scientists. So there's this option on the Linux kernel bootline that basically restricts which cores certain timekeeping interrupts are run on. So by default, the Linux kernel will call about 1,000 times a second certain timekeeping interrupts, and that can really have a big performance impact on certain applications. So by specifying this no hertz full option, you can turn off these interrupts on most of the cores. You got to leave it on 1 or 2 cores. And so for Stream Triad, it gives you about a 3% performance boost, and for our application, we get about a 5% performance boost. And that's not negligible. Okay. So another quick thing. So the AWP-ODC-OS stencils use 8 single precision divisions. So that's throughout all of the kernel. So every time step update, you need to do 8 divisions. You can't really get rid of those. So that hurts performance quite a bit. So it was noticed using VTune that we've got these pipeline stalls coming from these divisions. So we replaced the divisions with the reciprocal 28 approximation instruction and a multiply as well. And that gave a performance increase of about 7%. And we also see a corresponding decrease in the CPI rate. I mean, the CPI rate decrease follows from the performance speed up because the CPI rate is determined by performance and number of instructions. The performance dropped by 7%, the number of instructions went up by 2, so you can calculate this number directly. But it just suggests CPI rate is a good proxy here for performance. Okay, and then finally, last point is something about legacy serial code. So the lesson here isn't that serial code is bad, because that's not much of a lesson. But like Lars said yesterday, on Xeon Phi on Xeon Phi serial code really does hurt you particularly badly, often for surprising reasons. So we had this code running on the GPU version that's serial in the initialization part of the code, and it wasn't so painful there. But then going from the GPU systems with 6 gigabytes of memory to a Xeon Phi with 16 gigabytes in flat mode, or 60 in cache mode, or even more on PETA up to 190 gigs, that's a huge increase in the amount of data you need to process. So it was manageable on a GPU system, but now when you're processing 60 gigabytes worth of initialization data, that's a 10 times increase in the number of data you need to process. That slowdown becomes very painful. It's amplified also by the fact that single Xeon Phi cores aren't that great, right? So in total, you get about a 30 times slowdown, and we're seeing initialization times of 20 or 30 minutes, which was particularly painful. So it took about 20 minutes to fix, but it really made a big difference for us. Okay, and then something about VTune, but I think I'm out of time, so I'll skip that. Summary and conclusions. So I've talked about this AWP-ODC code, which is a Seismic code, and we've tuned it to run on the 72XX. The vector folding has given us a performance speed up of 1.6. And this vector folding technique can be applied really to any stencil code. So if you've got a stencil code, you should look into that. Cache mode is a viable option. We get about 94% of flat mode performance. That's great. And the main takeaway is the KNL code is outperforming the top of the line GPUs, which for us is the most important thing. So that's it. Here are some references and the all-important optimization notice. And any questions?
I think we've got time for probably one or two questions.
I'm puzzled. If you have a 13-point stencil, I would expect, in principle, if the cache was infinite capacity, you should have a 13-to-1 reuse factor on the right-hand side. You seem to be budgeting for everything coming from the MCDRAM, where if you have many points in the stencil, each point fetched contributes to 13 neighbors.
So I'm assuming you're streaming through the data in the Z direction. So let's talk about L1 cache for a second.
So I would say don't. Why not use something like the Mortenord or some kind of cache blocking scheme?
So even a cache blocking scheme, unless you're doing L1 cache blocking, which is too prohibitive, I think, in size.
L2.
Sorry? L2. So that's true. You can do L2 cache blocking, and then all of these things aren't out of MCDRAM. But this works in the level of L1 cache. So there is still a performance speed up there. Make sense?
In the beginning slide, you showed how much capacity you need over time.
Yes.
So is that to run on higher resolution models, larger models? I mean, and how long do these models run? I mean, what are you, constrained by now? And, when you look at what you're trying to take advantage of.
Sure, so that's a good question. So one aspect is, like I was saying, with the frequency. So to capture the effects of damages, you want to capture higher frequency components, which involves subdividing your grid. Even the same region has to be sampled a lot more finely. That drives up your computational cost. The other thing is adding new physics. So this guy here, so the slide is a bit out of date. It kind of stops at 2013. But so plasticity here is physics recently added to the GPU version. That's more physics, which means more computation, so it's slower. So to add more physics and things like that. I mean,
full runtime for one of your,
depends on the number of nodes. For example, the M8 simulation was running on about 250,000 cores for a full day. So
Let's thank our speaker.